All right, is the mic on? Yes, can you hear me? All right, how many got started on the homework? Did you have trouble with it? I saw some traffic on Piazza. I've been trying to keep up. We doing okay? So far, so good? Okay, so Lab 9 was graded last night. I apologize. I started getting notes from students saying, I'm sure I turned it in, and there was no solution there. So I looked and spent some time trying to figure it out. And what happened apparently is I downloaded the submissions during the day because I was debugging the autograder. And of course, some of you hadn't had labs yet. So many of the ones that were missing were from the later afternoon labs, which sort of gave me a clue. Turns out that the version I had downloaded earlier in the day was still there. And the one I was downloading was being renamed to avoid overwriting the first version. I didn't see the second version, so I graded the wrong version of the file. I apologize if it gave you a little minor heart attack, but they should have all been graded the second time yesterday. And that's why you'll see that those of you who were in the earlier day sessions, you'll see that there are 2 uploads to your assignment. They're the same, they were just different runs. All right, for homework 2, I've seen a lot of traffic on Piazza so far. I think that's good. If you can, post it publicly rather than privately. Only make it private if you're posting your code. If you're just posting questions about how should this work and so on, be explicit and try to make it public. That way everybody can share. And I very much encourage and appreciate the students who answer each other's questions. Sometimes I think that trying to explain something is the best way to learn it, and I think that that's actually a positive. So if you feel like answering a question, by all means, go right ahead. Your posts, I believe, when you answer a question will be or can be made anonymously, and so you should be able to click on anonymously if you don't want to leave your name. Okay, midterm 3 is Friday, April 15th. It will focus on one thing and one thing only. It's just going to be on object-oriented coding. So you'll notice that on your calendar, some readings popped up on object-oriented, the sort of object-oriented philosophy from Think Python and Python for Everyone. You should, of course, read those readings. We're going to start developing something in an object-oriented sort of fashion. Like I mentioned before in this class, we started with a sort of very functional approach, kind of like functional programming, where we don't use a lot of assignment statements, we don't use a lot of temporary variables, everything gets calculated and returned. And then we moved to a more imperative style. That's when we started using sort of the traditional for loop that so many of you enjoy. That's a more imperative style of programming, and now we're going to talk about object-oriented style. You need to be conversant with the 3 styles and understand their differences. So we're going to try to be as object-oriented as we can on this next thing we're going to start today. We will cover analysis of algorithms on the final exam, which will be comprehensive. So everything's game on the final, which takes place, I think it's the 13th. I don't remember. I posted it in the last class. Now, I have to admit there's a little bit of a personal reason to have the exam on the 15th. I normally would have waited maybe a little bit longer, but I'm not going to be here the 15th. So the fact that I'm not here means that the TAs can run the exam without me and you don't miss a lecture. So it's a little bit of personal convenience, but I'm going to be, actually my daughter's getting married on the 16th, so I'm going to be gone. But I'll be back on the 18th, so bright and early, so we'll see you then. All right, Lab 9. Lab 9 was meant to sort of drill you on these notions of iteration and recursion and make sure that you keep some facility or gain some facility with these concepts. So I gave you the same problem 3 times. The problem was take a list of integers and return a new list containing integers which were divisible by their predecessor. So this is to make you play with the start and end of iteration and the start of end of recursion. And you need to be really careful on this about the endpoints of the iteration if you're writing the iterative version. Factor next 1, of course, was the one where you were asked to use a comprehension. So here's my solution. You'll notice I use a docstring just because I remembered to do it. By the way, there were questions about homework 2, should you be commenting? You don't need to remove or change the comments that occur between functions, but you are responsible for commenting your code in the functions. In particular, you use an assignment for a temporary variable. Tell me what the temporary variable holds. You're going to make a conditional statement that tests some condition, explain what that condition is actually testing. Don't just repeat the condition, say it's testing to see if x is equal to 0. Tell me something that's meaningful in the context of the m-index. Checking for an m-index or a list that has no shared meals or something. Give me the context for which that condition is holding. All right, so this is a pretty straightforward comprehension. The one thing we have to worry about, of course, is the end. And you'll notice that I've made a decision here to check for modularity, in other words, evenly divisible, by looking back by 1. So I'm looking backwards here. And since I'm looking backwards, I can't start in the usual starting position of L0 because I would be comparing L0 with the last element of the list, which is not called for in the spec. In the spec, it says within the list, look for comparisons. And that means that I'm going to make one less than the number of list comparisons. So I need to shorten my range. So this is a pretty straightforward one. I'm going to use the, essentially I'm going to build new structure, so the comprehension is very appropriate. The use of this filter to collect only the things that matter means that the construct that's returned may be shorter than the template, which in this case is this range. And we all know that. So this is the cleanest, most straightforward implementation of this kind of pattern I can think of. Questions? Factor 2, same exact problem, but this time don't use a comprehension. Well, it's a lot of solutions. Here's the one that's sort of immediately obvious. It's a rewrite of exactly the comprehensive case using that pattern, that accumulation construct, where you start with an empty thing, and as you step through that same range and make that same comparison, you append whatever you meant to append to that empty thing, and then at the end you return it. So this is just a rewrite of that comprehension. It's doing exactly the same calculation in exactly the same way. Okay? Factor 3, well, there's a lot of these. In this particular case, you've probably noticed a couple of different types of recursion, at least 2 types of recursion. There are many more, actually, but the 2 types of recursion you may have noticed is sometimes the structure we're recurring down is just a list. It's a flat structure. And we're just doing something to every element of the structure. In a sense, that's when recursion most looks like iteration. This case, for factor next, that's what we have, because we're actually stepping down a list. We're going to do exactly the same comparisons we do with the iteration, but we're going to do them recursively. Now, other types of recursion that you've had is where the structure itself has some nesting, and then the recursion not only steps down the list or steps down the structure, but also descends into elements of the structure. And that's one that's much harder to do iteratively. That's when you sort of have to use recursion to be able to traverse all the elements of the structure. Here, this is the easy kind. The easy kind has a name. It's called tail recursion. It's called tail recursion because every recursive call typically deals with one less element of the list. So the list keeps getting shorter. You trim away the front of it, and you get the shorter tail every time. And you operate on that shorter tail. That's the sort of the idiom that gets used. Inside a machine, in a compiler, in a good compiler, tail recursion is recognized and converted to sort of very tight iteration at the machine code level anyway. So it's indistinguishable essentially from the iterative code at runtime. So here's my tail recursive formulation. Again, I have to be a little bit careful. I've got to operate on 2 elements at a time, right? So here, I've got to operate on my on the tail, where I compare the first element to see if it can evenly divide the second element. So I'm going to do it here. Notice the numbering. So this is the second element evenly divisible by the first element? If it is, then I'm going to essentially add that first element to whatever this factored x3 on the tail returns. So the thing that I'm returning here is a list. You can see that in the base case. When my length gets down below 1, below less than or equal to 1, I don't have 2 elements to compare anymore because the list has only 1 element. Then I'm returning the empty list. This is like saying a list L of 1 element has no elements that are evenly divisible by their predecessor because there's no predecessor. So I return the empty list. And then as I back out of this, that empty list gets returned here, and the element that evenly divides its predecessor is added in front of it. And as I back out of the recursion, I keep constructing that result list. On the other hand, if this is not the case, then I just return what's returned by the rest of this. So as I exit, I skip the case where I don't have the even division. And when there is an even division, I prepend the new element, and then that keeps becoming what's returned. So in a sense, I'm going to recursively traverse L, comparing those first two elements, and for that reason, I have to stop in the base case one shy of the end of the list. And as I go, I construct the result as I exit the depth of the recursion. Right? So I descend down the list, and as I compute the comparisons and collect the ones that are valid, I construct the list on the way out. So really interestingly, although it doesn't look that way to our eyes, the actual first comparison that's actually going to get done is I will compare these. I will sort of leave this thing here hanging pending while I descend the rest of the list. So while I construct each singleton element, the concatenation doesn't happen until I leave. Right? Because as I evaluate this thing, and then I'm going to evaluate this thing. I can't do that concatenation until this returns with the rest of the list. And so the concatenation happens on the way out. Now there's another way of doing this. Sorry, it should be a D. I could use a helper function here, and instead of building that list as I exit, I can sort of invert the recursion and build the list as I descend, build the results as I descend. And here I'm going to do it by carrying an extra argument, which is the result. And you'll notice that in the evocation of the helper function, I just passed the original list here. And here I have the empty list, which is my initial result. So I start to help. Everything here is the same. I have the same mechanism, except instead of returning the empty list, I return whatever R was. Here I have the same test, but here notice what's different. I descend down the list, so L becomes the rest of L, but I add the current element to the remainder of R, which I'm sort of building left to right. And then I pass this value into R, so R will have whatever the result of this comparison is will be prepended already. So here I'm building the result from sort of left to right as I descend the list. In the previous example, I'm building. What happened here? Oh, I'm sorry. In the previous result, I'm building the list from the end back as I exit the recursion. There are all sorts of other configurations that you can use for recursive formulation here. Anyway, this was just an alternative. Other questions? So I realized I left one out, didn't I? What was the last one? Perfect. I can show you that on Friday. It's pretty straightforward. You're just going to do a test over the range and see if the numbers all sort of add up. There's a sum involved in a comprehension. It's a one-liner. I'll show it to you, or even better, I'll post it on the website. I apologize. Okay. So where were we? So we were just starting the sort of object-oriented method. We discussed objects, classes, attributes, and methods. So we talked about how this is a class definition, how I use the uppercase to remind myself it's different than just a method or a variable. The class definition contains methods that refer to this mysterious self, which refers to the instance of that class that has the method invoked on it. Okay, we'll see this as we start building our solution today. And I gave you a few examples like A. When I invoke this constructor, which has the same name as the class, this returns a fresh instance of this class. And so A is a value, the value of A is something of type foo. And A.bar, which is a method invocation, you can see the little parens here imply this is like a function, but the dot says it's a method of the object of A. Invokes this function, passing A as the value of self and returning 0. And then we did some other examples where I referred to internal variables within the method and how these are all hidden within my method and class invocation, because all of these self methods are valid only within the scope of the class. So we did an example like this to show how they differ. So we're going to build a little example here, and then we're going to build a game. We're going to build Boggle today. It'll probably take a few lectures, but surely we'll be done by a week from today. And when we build Boggle, we're also going to do a little bit of user interface design, very crude, so we can at least play with the mouse instead of having to play with just the keyboard. So I'm going to define a class called point, which is meant to represent a point in two-dimensional space on the Euclidean plane. This is a common example for object-oriented coding. My class name is point, and there's an initialization function, which is, remember, this special function with the underscores is invoked whenever an element of class point is created. How do you create an element of class point? Well, you invoke the point constructor, which has the same name as the class. And it has, as usual, for every method, self as the first variable, and there are two optional values here, xval and yval, which I simply set to be the values of self x and self y. They're conveniently default to 0, so if I don't provide xval and yval, the point, whatever point I create, will have value 0, be at the origin of the Euclidean space. And I'm going to apply one function or one method called vlength, which is the vector length of the point self. And it computes the vector length by squaring x and squaring y, and then multiplying by 0.5, which is the square root of x squared plus y squared, which is the distance, the vector length, if you like, of where this point is with respect to the origin of the Euclidean space. So if x is 0, 0 squared plus y squared, which is 0, so 0 plus 0 raised to the half power is still 0, and the vector length at the origin is 0. So when I create a point instance, I can use the fact that I have these two values for the init function and just pass parameters in the same way I always have for a function, ignoring that self parameter, which is automatically bound to whatever the new object is, whatever that new instance is. So here I create an instance of the class point, an object, A, and if I look at A's vlength, it computes this to be 11.18, which I expect is 5 squared plus 10 squared divided by, or multiplied to the 1/2 power. I didn't check it, but I'm sure it's right. All right, so it's a lot cleaner here than having to sort of sit here and say, well, I'm going to create this thing, and then at the top level, I'm going to add an x value and add a y value. It's sort of the way we've been doing things. It sort of runs counter to that notion of object-oriented programming, where the only functional stuff that should have access to the internal of the point representation are the methods that are associated with that class in the first place. In other words, I'm not going to create an object of type point and then at the top level go attaching random stuff to it, right? And my favorite TV show right now, I'm watching, my wife and I are watching this old British show called MI5, and I'm not going to go and create a point object and then say a.tv equals MI5, because it doesn't make any sense, right? I mean, I can do random stuff like that, but it violates the spirit of the object-oriented paradigm. So this kind of, when you create a class, this kind of notion of making sure your initialization function sets up the internal variables you're going to use, and that these self-internal variables are only and ever referred to by the methods that are attached to that class, that's good practice, right? It makes the code more maintainable. You can examine it in isolation from how it's used. You don't have to worry about somebody coming in and sort of messing with your code from the outside world. It's all nicely encapsulated in private. You may remember we briefly talked about promiscuous variables. Object-oriented is the opposite, doesn't like promiscuous variables. It doesn't want you doing anything that you don't have a right to do. It wants to sort of keep things private. That's the theme. Any violation of that theme, you're sort of departing from the object-oriented paradigm, and you lose some of the advantages of writing true object-oriented code that way. So we're going to build a game. How many of you played Boggle? Who doesn't know what Boggle is? Anybody not know what Boggle is? You don't know what Boggle is? Oh my God, you guys do not do word games? What's wrong with you? Let me find a picture of Boggle online, just because you should see it. This is so when I was a kid, when I was in high school, I got my first job, which was at a public library. I was a page. That's what they call them. You know what a page is? It's the person who shelves books. Not very exciting. So I spent my life shelving books, and I got to know a lot of librarians who were mostly older women. It was predominantly female. A lot of grandmothers worked at the library, and they were mean word game players, and I kind of got hooked with them. Crosswords, Boggle, those kinds of games. They were really good with language for the most part. This is what Boggle looks like the way I learned it. And you'd buy it in a little box. I have one at home. It's a little tray, and there's 16 die, and the die have letters on them. So there's all the letters of the alphabet on these die, and there's like a plastic dome that covers this. And the way you play Boggle is you put the die in there, you shake it up, you turn it up, and the die fall into place in the grid. And then you remove the cover, put it in the middle of the table, and start the timer. And the objective of the game is to get more words than everybody else. And how do you get words? Well, you start in the puzzle wherever you want to start, and a word has to have adjacent letters. So, for example, G-E-T, this is a word, right? G-E-N-T, gent, is a word. W-E-N-T is another word. S-E-N-T is another word. So they have to be adjacent, either left, right, up, or down, or diagonally. And it turns out you can actually get quite a lot of words in the time that the sand runs out. And then when you're done, you each read off your word list, and if anybody else has the same word, everybody crosses it off. And so you win the game by having the most unique words. All right? Everybody sort of get this? So that's the game we're going to play. By the way, there are variants here of the game. In some variants, you can reuse a letter, like the E could be used twice. G-E-N-E is a word. In other variants, that's not allowed. The stricter variants, you have to use the letter only once. Okay, so that's Boggle. And the rules are available online. You can just look it up on Wikipedia, which is what I just did now. So you roll these special die, you arrange them in a 4x4 grid. The faces present a grid of letters, and you find words starting anywhere in the grid using adjacent letters only, where adjacent is vertically, horizontally, or diagonally. Now we want to build this game so that we're actually going to play against the machine. The machine will always win, by the way, but we'll play anyway, see how many words we can get. We'll change the rules a little bit, because the computer is going to find all the words. You're not. So we'll score you based on the percentage of the actual words that you find of the available words. So I stole the original configuration from a game I have at home, and this I'm going to provide here. There are 16 die in Boggle, not surprising because it's a 4x4 grid. And each one of these strings corresponds to the letters on the faces of one of those die. So we're going to represent each die as a string of 6 characters. Thanks to the game designer, which I misspelled. Man, I'm not having a good day. The character frequency here, just eyeballing it, there's a lot of E's and a lot of A's. And I bet if you find the one Q in here, because there is one, where is the Q? Second to last word, there's the Q. It unusually has the U with it, but if there is no U somewhere else, it's useless, right? So there has to be at least some other U in the puzzle. So it sort of respects the frequency. This is the genius of the game, is that the collection of frequencies in the die make it possible to have a good number of words. Otherwise, you could make this game very easy to play if you had no vowels, for example, or if you had very few vowels. Now, what we're going to do here is we're going to use our 57 element 5-letter word list that we use for the word ladder. We're going to use this for Boggle. That's our underlying solution set. Now, it doesn't mean that, so it places 2 restrictions on the game for us. First of all of our words are 5-letter words. It's kind of unnatural, right? The second restriction is that, so they're all 5-letter words, And only these words will be allowed as solutions. So it makes it a little bit easier to find what solutions are actually embodied in any board. Realize that of these nearly 6,000 words, only a small fraction will be found in any roll of the die. Right? There won't be 1,000 words. There will be a couple, 10, 15, 20. So how do we do this in an object-oriented way? Well, our general strategy is we're going to create a new class called Boggle. And that class is going to have a collection of methods that manipulate the board, do things like read in the word list, shake the die to start a new game, check for solutions to make sure they're actually legal solutions that are found on the board, that kind of thing. And we're going to do this by encapsulating some data structures which represent the state of the game in our new class. So here are the data structures we're going to have. The first one is the board. This is what the current puzzle looks like. So when you roll the die, which we're going to have to do, we're going to have a method that rolls the die and populates the board. We're going to have some legal configuration of the 16 die that I showed you before. We're going to have a list of words, the master word list, which we're just going to read in from the file. And by the way, if you choose not to use the 5-letter words, you can take a dictionary. You'll find on the web, you'll find many dictionary files, crossword puzzle, word lists, that kind of thing, that you can use with this game. So you don't have to play with just Knuth's words. You can play with any dictionary list. Then we're going to have a local variable, or instance variable solutions, which will contain the words found in the current puzzle board. So I create my Boggle object. I'm going to have some method that shakes it and creates the board layout, that populates the board from the dice that we described before. And then once the board is laid out, I'm actually going to solve the puzzle. I'm going to write some code that looks at that board and derives every legal word from words, the master word list. Every legal word in that puzzle will be found. And I'm going to put that in a list of legal words. That simplifies things because, you know, if Adi's playing the game and he says the word is bento, I don't have to go look at the puzzle and try to figure out where he found it. I can just say, no, that's not in the solutions I found. It's not there. Because I know that my code will find every possible word from the words list that's in the current puzzle. By the way, this is the hard part. One way I don't want to do it is to consider every word in the master word list and see if I can find it. That is not the approach we're going to take. Finally, we're going to have this funny variable called legal prefixes that will tell me all of the legal prefixes found in the current puzzle board. And I'll explain what this is later, but it's a data structure that's going to help accelerate the game. It's going to help us play the game in a reasonable way. And then finally, because this is a video game, we're going to have a cheat mode bit that I can set where Boggle will tell me what the solutions are in the board. And of course, I have all these data structures. Somebody has to set them up. And what we're going to do is we'll use the constructor, which is the fancy name for that init method, the underscore init underscore method, to create the data structures at game creation time. Okay, so let's go to a sort of a quick demo here. That's good enough. So this is my solution. We're going to run this. Oh, it's running it in a different, it's running it in a different place. So this is just idle, and this is not the version of the game that has a user interface. So we have to sort of make up some way of playing interactively by typing. So you'll see some stuff here along the way. The first thing you see is this sentence says read 5757 words. By the way, the starting thing in this file at the very end, the main part that gets run when you run the code, all it does is it creates an object of type Boggle. And by creating an object of type Boggle, it creates all the internal structures, and then it plays the game. So you'll notice this output that looks a lot like the output from read words that we used in WordNet. That's because we're going to rip off that code and use it here. And then we have this puzzle contains 7 legal solutions, and then this funny cheat thing here. This is obviously the cheat bit was set when I invoked Boggle, so it's showing me the solution. That's so I can make sure that I've developed it correctly. If I were really playing the game, of course, I would probably turn cheat mode off, because what's the fun of knowing what words are going to be found? Then there's a little bit of helpful input here. It says, you input your solution by giving row, column, row, column, row, column, which is a path of series of row, column coordinates. So here they're presumably 0, 1, 2, 3, 0, 1, 2, 3. Certainly doesn't give us much information. We should say where the origin is, but that's what I would guess. Of course, the origin could be down here, it could be up here. You know the difference, right? So when you take math, the origin is in the bottom left of anything, right? Because we think of being in the upper right-hand quadrant. In computer graphics, the origin is the top left corner, and everything goes down. So this is the positive direction is down. And the reason for that is because early graphics code was written for teletypewriters. And as the paper advances, you would sort of print things down. And so that's why the origin of your screen is upper left rather than lower left. All right, let's just take a look at one of these. Radon is in here. Can I find radon? There's R-A-D-O-N, so yep. How about moron? M-O-R-O-N. Bingo. Irate, I-R-A-T-E. So yeah, so it seems to have found the words in they're finding them. Okay. So let's see if we can play the game. Let's see if I have the row column coordinates correct. So somebody help me out here. Let's take adorn. That should be 1, 1. And then D should be 0, 0, 0, 1, 1, 2, 0, 3. No, 0, 2. Yep. So I did it. So 1, 1 is A, 0, 0 is D, 0, 1 is O, 1, 1 is R, 1, 2 is R, and 0, 2 is N. And so adorn is added to my list. I can redisplay the board if I want to see it again. I could show what I have so far. I can ask for a new puzzle. And when I ask for a new puzzle, it tells me, oh, this is too big to, where's my mouse? When I ask for a new puzzle, it tells me, wow, you found 1 of 7 possible words, you're kind of a loser. The new puzzle has 31 legal solutions, so the puzzle itself is a lot more interesting. Okay? Everybody clear on what we're shooting for? Is that good? Questions? All right, so. All right, so a couple of observations. Compared to the imperative or functional style that we've been mostly using now, there's kind of an emphasis here on not seeing stuff passed around as arguments. So recall when we discussed promiscuous variables, I said don't create variables in the read eval print loop at the global scale and then just access them from within your function, because you don't know who else is accessing your variables. That's what makes them promiscuous. So we emphasized in the imperative style, you pass stuff around and you operate on stuff that's given to you. You don't go outside your boundaries. In the object-oriented world, we enforce that same constraint not by passing stuff around, but by keeping those variables within the object to which the method is attached. If I don't pass a lot of stuff around, I mean, some passing is inevitable, but if I don't pass a lot of stuff around, then I'm constrained to using just my own variables. And I accomplish the same kind of thing. So class and its methods, they form this context that everything inside that context is shared within the method and within the variables, right? As a method or as the variables within self. Now, in some object-oriented languages, anybody want to guess? Some object-oriented languages, you distinguish between things that you keep private and things that you're willing to share. And this is more or less declared by the programmer, whether you want something to be private or whether you want it to be shared when it's within your object, the object that you're writing or the class that you're writing. Python doesn't have that. Python lets you access anything you want. Python is the language where something that's an integer now can become a string later, and can become an object after that, or a list, or whatever you like. So Python's pretty forgiving that way. It doesn't have a lot of typing going on. And the same thing applies here. We have this notion of an object with its variables safely encapsulated inside. But in practice in Python, you can be as promiscuous as you want. So you gotta here enforce these constraints implicitly by discipline. Now, discipline is hard, right? So when I first started coding in C years and years ago, it wasn't my first language, but it was one of my first languages, C++ came out. This was kind of in the 80s, and it became a big thing. Everybody became really object-oriented. It was like, wow, that's the future. We're going to abandon C, we're going to write C++ because it's so much better. Later, we abandoned C++ and wrote Java because it's even better than that. And so on. I mean, this is an eternal thing about CS. We're constantly abandoning stuff and inventing new languages. But at the time, I remember thinking that the whole idea of encapsulation in C++ was actually kind of dumb, right? Because there was nothing that C++ could do. I mean, there's stuff that C didn't have, templates and things like that. But the whole object-oriented idea was perfectly implementable in basic C. All it took was a little bit of discipline on the part of the programmer to associate data and functions that would not be misused in any other way, and that you couldn't just reach out and grab somebody's data and make changes to it. And if you just enforce that discipline, if you look at large C programs, you'll notice that stuff is distributed over many, many files. Right? Little pieces of code live in their own file, and the actual project has hundreds or sometimes thousands of files of C code. That's not accidental. That's the programmer trying to enforce by discipline what object-oriented languages enforce to some degree, not always completely, but to some degree by fiat. And so that's why C projects have so many files. But more to the point, whatever's public and whatever's private is part of the spec. So if I give you a specification and say, these variables are not to be touched by anybody outside of this class, then that's the way they're supposed to be dealt with, even though Python would allow it. So let's get to the point with the constructor. So I'm going to define a class Boggle. There's my constructor. It's a method of the class. It's usually by convention the first method in the class definition. It always has the self variable, which refers to the object that's just created. I have two optional arguments. The first one is the input that tells me where the solution words come from. I'm going to use that same words.dat file we used before. And then I have a variable called cheat, which is initially set to false, which is the cheat flag, which sets the bit that lets me see what the solutions are once the computer identifies the solutions. And then the constructor, it simply goes through the steps to set up the internal variables that we need. So the first thing we'll do is we'll invoke the readWords method with the single variable words.dat, which is the default value for input, unless I were to create Boggle with a different default value or a different value. So this sets up that internal words list that I have for all the words in my dictionary. Then I'm going to create, then I'm going to create the board with a random puzzle. So I'm going to create new game, which basically takes the die and rolls them, and then it creates the representation that I can see in the printed puzzle. When I'm done with that, I'm going to call self.solve, which finds all the legal words from words, readWords, all the legal words that are embedded in this roll of the puzzle. And then if cheat mode is on, I'm going to set the self.cheat bit so I know I can govern the solution, how the puzzle is prevented. And finally, I'm going to call self.play. And from your knowledge of homework 1, what's homework 1 again? Was it a card game or something? There was a play function, right? That's what this is too. It's the one that manages the interaction with the user. And when we finally write the user interface using the TK interface, we're going to replace this play method with one which invokes the interactive part of the game. Okay? So let's take a look at readWords. I'm just going to rip it out of WordNet, the WordNet code that we saw before. It's a method. It's part of the Boggle class definition. It has one argument, file name, which you recall from before is the input, which is passed to the constructor. And if it's not passed to the constructor, it's simply words.dat. Notice that here I don't need a default value. Why? Because read words will only ever be called by this constructor. In fact, there's nothing that says I can't just open code read words in the constructor itself. But why would I do that? It seems to make sense to create a method that does just one thing and does it right, and then just invoke that method. And so that's what we've done. It's an organizational principle when you're building a design for an object-oriented project. So I'm going to open that file. I'm going to simply read, infile.read, reads in the whole file, lowercases it, splits it, I ran off the edge of the page, splits it by the, with no argument to split, splits on the new line, and then it returns the list here of all the words with the extra spaces stripped off them. So this is a comprehension that reads in the whole file, produces a list of words. I remember to close the file handle. This is a file handle to the open file. I'm going to close it after myself. And I'm going to print out that same message I printed out in wordnet.py. This is essentially the wordnet.py read words. So that additional parameter file name is passed during method invocation. So when I say b.readwords words.dat, we saw that already right here. It's passed to input, which gets its value from the constructor or from the default value words.dat. Okay? Everybody follow? We good? Also, one thing to note here is that no values are returned, and that's pretty typical. Unless the method is an outward-facing method, something that somebody else is going to invoke, maybe to interact with the puzzle or to ask about the puzzle status, it rarely returns anything. These functions don't return any values. Instead, what they do is they manipulate the internal variables by essentially passing stuff by sharing internal variables to the object. That's how these methods share stuff with each other. We don't need to be passing stuff in the command line or in the signature of the function because these things are all part of the same tiny little context. Okay, so I want to go back to our game here for a second. I have a different. So this is what we have so far. I've changed the init function to just have read words in it. Otherwise, it's exactly what we had before. And here's our read words, the method we just saw. So this is the state of my game so far. And I want to run this to show you some interesting stuff, presumably. Okay, so I have a class definition. I'm going to create an instance of type Boggle. And because we saw, as we just saw, there's really only one thing going on in the constructor, and that is to read in the words, I get the familiar method that says I've read in those words. I can now notice from outside I can access the first 10 words of the word list. I can check the length of the word list. And they're all there. Okay? But here's something that's a little bit awkward. When I simply type B, I get this kind of impenetrable representation. That representation is basically telling me this thing B, the value of B, is an object of type Boggle. That's the type of the object. The main __ main tells me where the Boggle class is defined. It's defined in the main context. And then this thing here is actually the memory address of that object. So what does that mean? Well, let's try creating another one. You'll see that it is also an object of type Boggle, but you'll notice that these values differ. So this is essentially a memory location where the object of that particular instance of the class is stored in memory. It's how I can tell them apart. Each of those memory locations has pointers that have different locations for the corresponding variables. So the board for this game can be different for the board for that incarnation of the game. Now, this printed representation of this thing is not very useful. And it begs the question of what should an object look like when I print it out? We know from our work with lists and strings that when I have a list L and I just type L, I actually get a nice printed representation of the list. I don't get something that looks like this. I don't get something that says main.listObject at some location. I get a nice printed representation. It's a beautiful property. And that beautiful property is if I take that written representation and type it back into Python, it will create a list just like that. I don't have that ability here, right? We know that this notion of having something printed and having something that I can sort of read back in to recreate the thing, we've seen this before. We saw it when we talked about strings. You may remember that when I had a string with a \n in it, the value of that variable that was the string had quotes and the \n in it. But if I printed that variable, the quotes disappeared and the \n became a carriage return. So we have this distinction that we haven't really studied in class and that confuses a lot of students. And that distinction is, what is the distinction between the printed representation of something, and the representation that can be used to recreate that something? So let's go back to this for a minute. When I print something, ideally we want that printed representation to be something that you see as a human and you can understand. For the Boggle game, what would I like to see if I type B? What should the thing look like? Should it be that pointer? My preference would be that I get a 4x4 layout that shows me the grid of words. That's the thing that's most useful to me as a human from a sort of game playing perspective. I want to know what the state of the board is. So, however, when I print something to a file instead, rather than to the user interface, I would really like something that could be interpreted by Python and reconstructed. So let's say I'm playing Boggle and it's time for dinner and I want to keep the state of my game. I might want to print that Boggle not to the screen, but I might want to print it to a file so when I come back I can have Python reload that file and restore the state of my Boggle game. That would be ideal. But even that printed representation, which may not be nice for humans, it's not, this object representation I'm seeing here is not that either. It's a third way, which doesn't really help us either way. So we've seen this distinction before when I have a variable s which has a value as a string. If I simply ask what is the value of s, the value of s is this string thing, which by the way Python can read and reconstruct. But when I print s, the thing that I see is the printed representation of that string, which Python can't read and reconstruct, but is more useful presumably to me as a human reader. Yes?
If you made a B3 that was like equal to B2, then you modified B3, but it then modified B2 because like
if I make the B3,
like make a B3 variable that was equal to B2.
yes.
And then you modify B3. Would it then modify B2?
Yes, because it's just like a list L. If I make a L1 which is equal to L and I modify L1, I don't add to it, I modify it, then L will also change. It's exactly the same thing. That B is a reference to the object in memory. Just like that L is a reference to the list, which is an object in memory. But not like the x equals 5, which is not a reference to a memory location, but is an actual value. And that's the sort of basic distinction between something that's a value and something that's a reference. Okay? Unlike some other languages, in Python, a variable that's set to an object is always a reference. You can't make it otherwise. And a variable that's set to a value is always a value. You can't make it otherwise. Okay? So we've seen this distinction before. And the difference is, the reason we have these differences, sort of the thing that the incarnations of these differences are two functions, str and repr. So there is this str function which takes my value s and produces a printed value of that string. But the repr_s function, notice what it does. It takes that string and it encloses it in additional quote marks. And each of those escape characters is a self-escaped. What this is the value, which itself is going to be a string. This thing will be a string that, when read by Python, reconstructs the original string. So string is a string that I'm dealing with, and the repr is sort of one step removed, so that I can, so whatever it produces, I can evaluate when I read and reconstruct the original string. For objects, we have exactly the same thing. There are two built-in methods, str and repr, that go along with the object. So the two things have different interpretations. The str function or method, if present, is what gives you that human readable form. The repr function, when present, is what gives you something that can be read by Python to reconstruct the game. We're going to do both here. This is an important distinction. So we're going to do both of them and try to make our game not only pleasing to look at, but able to be written to a file and reconstructed on reloading. Okay, we'll stop there. We're out of time. We'll pick it up on Friday.